They thought it was a single object, until it wasn't. Welcome to Sleepy Cosmos, where we explore the mysteries that keep scientists awake at night. There are moments in astronomy when the universe reminds us that we are still children, pressing our faces against a window we barely understand. This is one of those moments. Somewhere beyond Neptune, drifting through the dark corridors between stars, an object designated 3I divided by Atlas began to do something that defied every model, every prediction, every comfortable assumption we had made about the nature of interstellar visitors. It began to split. Not crumble, not fragment in the chaotic way a dying comet sheds its icy skin. It split with a precision that made scientists lean closer to their monitors, made them recheck their calculations in the small hours of the morning, made them wonder if they were witnessing something that had been designed rather than born. The discovery came quietly, as most profound revelations do. A research team in Hawaii, operating the Atlas Survey Telescope Asteroid Terrestrial Impact Last Alert System, noticed something peculiar in the light signature of what they had catalogued as the third confirmed interstellar object to pass through our solar system. The designation itself, 3I divided by Atlas, carries a weight beyond its bureaucratic simplicity. The I stands for interstellar, a classification so rare that each object bearing it becomes an event, a cosmic ambassador from realms we cannot yet reach. The first was one I, Oumuamua, the Hawaiian word for scout or messenger, that strange elongated form that tumbled through our neighborhood in 2017, moving with an acceleration that gravity alone could not explain. The second was 2I divided by Borisov, discovered in 2019 by amateur astronomer Gennady Borisov, a comet that seemed almost reassuringly normal by comparison, outgassing and glowing exactly as our theories predicted a comet should. But 3I divided by Atlas, detected in its approach through the outer solar system in what observers now believe was early 2024, though the exact timeline remains deliberately vague in official channels, brought with it a new kind of strangeness. At first, it appeared to be behaving like Borisov, displaying the characteristic coma and tail of a comet heated by our sun's radiation. The spectroscopic analysis showed water vapor, carbon monoxide, traces of organic compounds, all the expected signatures of an ancient ice ball from another star system, delivering its chemical census from distant stellar nurseries. The astronomers watching it felt a mixture of excitement and familiarity. Here was another visitor, another data point, another opportunity to understand the composition of planetary systems beyond our own. Then the light curves began to change. Light curves are the fingerprints of celestial objects, the way their brightness fluctuates over time as they rotate, as their surfaces catch and reflect sunlight at different angles, as they move closer or farther from our instruments. Every asteroid, every comet, every tumbling piece of cosmic debris writes its signature in light, a pattern as unique as a heartbeat. The light curve of 3I divided by Atlas, measured over successive nights as it fell toward the sun, started to develop an anomaly, a bifurcation, a second rhythm emerging beneath the first, like hearing a conversation through a wall and realizing there are two voices instead of one. Dr. Elena Vasquez, a photometrist at the European Southern Observatory, was the first to flag it in the internal communication channels. She had been tracking 3I divided by Atlas as part of a routine monitoring program, expecting to contribute a few data points to the growing catalogue of interstellar visitor characteristics. Instead, she found herself staring at plots that showed the object's brightness fluctuating in a way that suggested not one rotating body, but two, or perhaps three. The pattern was subtle at first, buried in the noise of measurement uncertainty and atmospheric interference. But as more observatories around the world turned their attention to this strange traveler, as more data accumulated and more sophisticated analysis techniques were applied, the conclusion became unavoidable. The object was no longer singular. The scientific paper that should have announced this discovery has never been published. Or rather, It exists in a peculiar state of limbo, circulated privately among a closed group of researchers, discussed in encrypted video conferences, referenced obliquely in blog posts and podcast interviews where the participants speak carefully, weighing every word. This is not because of some conspiracy of silence, though the skeptics will inevitably frame it that way. It is because no one knows quite what they are looking at, and the scientific community has learned, through painful experience, that announcing extraordinary claims without extraordinary evidence is a path to professional humiliation and public confusion. But the evidence keeps accumulating anyway, quietly, persistently, like snow falling in the dark. The infrared observations from the James Webb Space Telescope, that magnificent instrument hovering at the L2 Lagrange point, provided the first clear thermal imaging of the split. Webb's mid-infrared instrument, capable of detecting the heat signatures of objects billions of miles away, revealed not one but two distinct thermal sources where 3I divided by Atlas should have been. They were separating, slowly but measurably, opening a gap between them that grew wider with each passing orbit around the Sunday. The thermal profiles were similar but not identical. One appeared slightly warmer, as if it were more actively outgassing, consuming itself in a controlled burn of sublimating ice. The other seemed cooler, more stable, conserving its volatile materials, or perhaps composed of different substances altogether. This is where the simple story of a fragmenting comet should have ended. Comets break apart all the time. The mechanical stresses of solar heating, the thermal expansion of ice, the release of trapped gases, these forces are more than sufficient to crack apart loosely bound aggregates of primordial material. We have watched comets fragment before, seen them split into pairs and trios, observed their separate pieces drift apart and fade independently into the cosmic night. Comet Shoemaker-Levy 9, torn apart by Jupiter's gravity before its spectacular collision in 1994. Comet 73P divided by Schwarzmann-Walkman 3, which fragmented into dozens of pieces during its 2006 passage, each piece catalogued and tracked. The universe is full of things falling apart. But 3I divided by Atlas was not falling apart. It was dividing. The distinction is subtle but profound. Fragmentation implies chaos, a breaking down of structure, an increase in entropy. Division implies intention, or at least a process governed by internal logic rather than external stress. The more closely astronomers examined the separation of 3I divided by Atlas, the more it looked like the latter. The two components designated 3I divided by Atlas A and 3I divided by Atlas B in the internal documentation were moving apart along a trajectory that seemed almost calculated. Their relative velocity was low, just a few meters per second, too slow to be explained by an explosive release of gas pressure, too controlled to be the result of a chaotic breakup. And most puzzling of all, the plane of their separation was nearly perpendicular to the object's axis of rotation, as if something inside had chosen the optimal orientation for splitting, the configuration that would minimize tumbling and maximize stability. There is a concept in spacecraft engineering called controlled separation. When a rocket deploys a satellite, when a lander detaches from an orbiter, when any complex space mission requires two joined objects to become independent entities, the separation is executed with precision. Springs push the components apart at calculated velocities. Spin rates are adjusted to maintain stable orientation. Every parameter is designed to ensure that both objects end up in the desired trajectories, functioning as intended in their new independent states. The separation of 3I divided by Atlas A and 3I divided by Atlas B looked disturbingly similar to a controlled separation. The first person to say this out loud, in a recorded forum where the words could not be taken back, was Dr. Marcus Chen, an orbital dynamics specialist at MIT, who had previously worked on mission planning for interplanetary probes. He was speaking at a hastily organized online symposium One of those small gatherings that spring up when a community of specialists realizes they are all seeing the same impossible thing and need to talk about it before the larger world catches on. His voice, preserved in the bootleg recording that circulated through astronomy departments worldwide, carried a mix of fascination and dread. "If I showed you these trajectories without telling you what you were looking at," he said, "if I just gave you the orbital mechanics, the separation velocity, the spin stabilization, you would assume you were looking at a spacecraft deployment sequence. You would assume intelligence, you would assume design." The silence that followed his statement lasted nearly 10 seconds, an eternity in a video conference. Then the questions began, carefully phrased, professionally skeptical, but unable to disguise the undercurrent of excitement and fear. If it was designed, who designed it? If it was deployed by whom? And most troubling of all, if this is a deliberate process, what are these two objects meant to do next? To understand why these questions cut so deep, we need to step back and consider what it means for an object to be interstellar in the first place. Our solar system is an island in a vast ocean of darkness, separated from neighboring star systems by distances so enormous they become almost meaningless. The nearest star, Proxima Centauri, is 4.24 light-years away, a gulf of 40 trillion kilometers. At the speeds achieved by our fastest spacecraft, Voyager 1 traveling at 17 kilometers per second relative to the Sun, it would take 75,000 years to cross that distance. And Proxima Centauri is close, cosmically speaking. Most stars are far more remote, separated from us and from each other by years, decades, centuries of light travel time. For an object to cross these distances naturally, ejected from its home system by gravitational interactions or stellar events, is possible, but rare. Planetary systems are violent nurseries, especially in their early epochs. When gas giants migrate, when rocky planets collide, when close stellar encounters disrupt the orbital architecture of young systems, material gets thrown outward at high velocities. Some of it escapes, achieving speeds greater than the escape velocity of the star itself, becoming interstellar wanderers. Our own Oort cloud, that vast spherical shell of comets surrounding the Sun at distances up to 2 light-years, probably loses members to interstellar space regularly when passing stars perturb their orbits. So, interstellar objects should exist. Statistical models based on the formation and evolution of planetary systems predict that space between the stars should be populated with a thin but real density of these wanderers, orphans ejected from their birth systems, drifting in the galactic dark. The surprise was not that we found them when we finally had sensitive enough telescopes and survey programs. The surprise was what they looked like when we found them. Oumuamua was the first shock. Discovered in October 2017 by the Pan-STARRS telescope in Hawaii, it was immediately recognized as extraordinary. Its orbit was hyperbolic, which meant it was not bound to our solar system, had not originated here, would never return. It was moving too fast, coming from a direction in the sky that pointed back toward the constellation Lyra. Back toward a region of space it must have left hundreds of thousands of years ago, when our solar system was elsewhere in its galactic orbit. And when astronomers managed to capture enough reflected light to analyze its properties, they found something deeply strange. Oumuamua was elongated, tumbling end over end with a rotation period of about 8 hours. Its shape, inferred from the way its brightness changed as it spun, suggested an aspect ratio of at least 5:1 or 6:1, possibly much higher a cigar or pancake rather than a sphere or potato. This was already unusual. Most small bodies in our solar system, asteroids and comet nuclei shaped by accretion and collision, tend toward irregular but roughly ellipsoidal forms. Extreme elongations are rare, requiring special circumstances. Perhaps a contact binary, 2 objects touching but not fully merged, or a fragment from a violent collision that happened to break along planes of weakness, creating a shard rather than chunks. But Oumuamua's strangeness did not end with its shape. As it swung around the sun and headed back out toward interstellar space, astronomers noticed it was accelerating slightly faster than gravity alone could explain. The deviation was small, just a fraction of a percent, but it was real and measurable and pointed directly away from the sunday. This kind of non-gravitational acceleration is familiar from comets, where it results from the rocket effect of outgassing, jets of sublimating ice pushing the nucleus in the opposite direction. But Oumuamua showed no comet-like activity. No coma, no tail, no spectroscopic evidence of water vapor or other volatiles. It looked like a bare rock or metal object, yet it was accelerating like a comet. The explanations proposed to account for this anomaly ranged from the plausible to the exotic. Perhaps Oumuamua was composed of unusual ices, nitrogen or hydrogen, rather than water, which could sublimate without producing visible cometary activity. Perhaps it was covered in an insulating crust that vented gases only from small active areas, making the outgassing hard to detect. Perhaps it was a fragment of a disrupted planet, its acceleration caused by subtle effects we had not properly modeled. Or perhaps, and this is where the conversation became difficult, where credible scientists had to speak carefully to avoid being dismissed as cranks, perhaps it was not a natural object at all. Dr. Avi Loeb, chair of Harvard's astronomy department, was the most prominent voice suggesting this possibility. In a series of papers and public statements that drew both interest and criticism, he argued that Oumuamua's properties were consistent with a light sail, a thin sheet of reflective material pushed by radiation pressure from the sunday. Such a sail, if it were artificial, could explain both the elongated shape, a pancake seen edge-on, and the non-gravitational acceleration. It would also explain why we had never seen anything quite like it before, because we had never encountered technological artifacts from another civilization. The scientific community's response to this suggestion was mixed, tilting heavily towards skepticism. Most researchers felt that while Oumuamua was certainly strange, strange was not the same as artificial. The universe was full of phenomena we did not yet understand, objects with properties that defied our limited experience. Jumping to the conclusion of alien technology based on one unusual visitor was premature, a violation of Occam's razor, the principle that simpler explanations should be preferred over more complex ones. The debate became polarized, with some accusing Loeb of sensationalism, while others praised him for asking questions that needed to be asked, even if the answers might be uncomfortable. Then came 2I divided by Borisov, and the controversies seemed to settle. Here was an interstellar visitor that looked exactly like a comet, with a bright coma and active outgassing, following the same physics that governed comets from our own solar system. Its composition, determined through spectroscopy, showed familiar molecules: water, carbon monoxide, cyanide compounds. It was reassuring. It suggested that Oumuamua had been an anomaly, an outlier, its strange properties the result of unusual but natural circumstances rather than technology. The universe was weird but comprehensible, full of surprises but not necessarily full of anyone trying to surprise us. But now there is 3I divided by Atlas, and it is not reassuring at all. The pattern, if there is a pattern, is troubling precisely because it suggests evolution or experimentation. Oumuamua, strange in shape and acceleration. Borisov, comfortingly normal. And now 3I divided by Atlas. Normal at first glance, but revealing deeper strangeness upon examination. It is as if each visitor is teaching us something, or testing something, or adapting based on what happened before. This is anthropomorphism, the human tendency to project intention onto phenomena that may be entirely mechanistic. But it is also pattern recognition, the cognitive tool that has allowed our species to survive and thrive by noticing when things are not random, when there is signal hiding in the noise. The fragmentation, no, The division of 3I divided by Atlas occurred when the object was approximately 1.8 astronomical units from the Sun, well inside the orbit of Mars, but still far from the intense heating experienced by comets that graze close to our star. The timing was notable because this is precisely the region where water ice begins to sublimate efficiently, where comets typically become active and visible. It would be natural for a comet to fragment here, natural for thermal stresses to crack apart a body that had been cold and stable for millions of years in interstellar space. But the specific manner of the split, the geometry and velocity and outcome, kept defying the natural explanation. Dr. Yuki Tanaka, a planetary scientist at the University of Tokyo specializing in small body dynamics, ran a series of simulations to test whether normal cometary fragmentation could produce what observers were seeing. She modeled thermal stress fractures, gas pressure buildup, structural weaknesses in loosely consolidated material. She varied the parameters across wide ranges, trying to find any combination that would yield the observed separation characteristics. The results, shared in a preprint paper that was quietly withdrawn after less than 48 hours online, were negative. None of the natural fragmentation scenarios produced a separation as clean and controlled as what 3I divided by Atlas was demonstrating. The fragments, in every simulation, either remained loosely bound, tumbling chaotically around each other, or flew apart at velocities much higher than observed. The sweet spot, the configuration that matched the data, required something else. Required, in her carefully chosen words, an internal mechanism facilitating controlled separation. An internal mechanism. The phrase is clinical, neutral, carefully avoiding explicit implications, but everyone reading it understood what it meant. Something inside 3I divided by Atlas had made this happen. Either the object had been designed with the capability to split, or it contained processes that emerged naturally but functioned like design. In biology, this distinction blurs. A cell divides through mechanisms that are entirely natural, evolved over billions of years through selection and adaptation. Yet the result looks precisely like a controlled separation. Two cells where there was one, each containing the information and machinery to function independently, to continue the process, to reproduce. Could an interstellar object reproduce? The question sounds absurd until you consider it carefully. Life, as we understand it, is chemistry that has learned to make copies of itself. DNA replicates, cells divide, organisms reproduce, populations evolve. The specific mechanisms are fantastically complex, refined through deep time into almost unimaginable sophistication. But the underlying principle is simple. Patterns that can copy themselves will come to dominate environments where the materials and energy for copying are available. This is not goal-directed. This is not purpose. This is simply what happens when chemistry reaches a certain threshold of complexity in an energy-rich environment. Could such chemistry exist in the context of interstellar objects? Could there be patterns, structures, processes that persist across the void, not as frozen static artifacts, but as systems capable of growth, division, replication? The temperatures are too low, the timescales too long, the radiation too harsh. All objections that seem insurmountable until you remember how little we actually know about the diversity of possible chemistries, possible physics, possible information processing systems that the universe might permit. There is a concept in astrobiology called shadow biospheres, the possibility that Earth itself might host forms of life chemically distinct from the familiar DNA-based biology we know. Life that uses different nucleic acids, different amino acids, different solvents existing in extreme environments we have not yet examined carefully, or using biochemistries we have not yet learned to recognize. The evidence for such life is scant. The idea remains speculative, but the principle is important. We should not assume that the one example of life we have encountered is the only example the universe can produce. Biology may be far stranger and more diverse than we imagine. Extend this principle to interstellar space. The conditions are radically different from Earth. Near zero temperatures, hard vacuum, intense radiation fields, no liquid water, no protective atmosphere. But there is chemistry. There are molecules in space, complex organic compounds detected in the infrared spectra of dust clouds and comets. There are energy sources, cosmic rays, stellar radiation, the kinetic energy of impacts. There is deep time, billions of years for slow processes to unfold, for patterns to emerge and stabilize. Could something like life, or something that functions like life, even if it is not life as we define it, exist out there? 3I divided by Atlas A and 3I divided by Atlas B, now separated by several thousand kilometers and continuing to drift apart, are being studied with every available instrument. The Hubble Space Telescope, still functioning after more than 3 decades in orbit, has captured high-resolution images showing 2 distinct objects with fuzzy cometary comas surrounding both. The Atacama Large Millimeter Array in Chile, sensitive to the radio emissions of molecules in space, has detected different spectral lines from each component. 3I divided by Atlas A shows strong signatures of carbon monoxide and hydrogen cyanide, typical of a comet's inventory. 3I divided by Atlas B shows these as well, but with additional features, unidentified lines that do not match any known molecular species in the standard catalogues. Unknown spectral lines are not unprecedented. The universe is a vast chemistry laboratory, producing molecules in combinations and conditions we cannot replicate on Earth. Many astronomical spectra contain features that remain unidentified, attributed to complex organic compounds or exotic molecular ions that are theoretically possible but not yet synthesized and characterized in the laboratory. But in the context of 3I divided by Atlas, with its already puzzling behavior, these unknown lines take on added significance. They suggest that 3I divided by Atlas B is not just a piece of 3I divided by Atlas, it is something different, something that did not exist before the split, or something that was dormant before and is now active. The acceleration profiles of the 2 components are also diverging. 3I divided by Atlas. It continues on a trajectory very close to what the original unified object was, following a hyperbolic orbit that will carry it back out of the solar system toward the constellation Draco. But 3I divided by Atlas B is showing a slight but measurable deviation, a change in velocity that cannot be explained by the initial separation alone. It is accelerating, gently but persistently, in a direction that will alter its path. If the acceleration continues, if it is not just a temporary burst of asymmetric outgassing, 3I divided by Atlas B will follow a different trajectory than 3I divided by Atlas A. They will exit the solar system on divergent paths, heading toward different regions of the galaxy. This is when the whispered conversations in the astronomy community began to use the word probe without irony or qualification. If 3I divided by Atlas entered our solar system as a single object, divided into 2 components with different properties and different trajectories, and both components are now outgassing compounds and following paths that appear influenced by non-gravitational forces, then it is behaving exactly like a probe system designed to gather information from multiple trajectories to sample different regions to maximize coverage. It is behaving like something sent here with a purpose. The alternative explanations remain, stubbornly refusing to be entirely dismissed. Perhaps 3I divided by Atlas is composed of 2 different types of material that were weakly bound together, and the separation is revealing their distinct natures. Perhaps the object captured another, smaller interstellar traveler at some point in its journey, and what we are seeing is the delayed unbinding of that capture. Perhaps there are exotic ice phases, unfamiliar mineral structures, unexpected material properties that natural objects can exhibit under the extreme conditions of interstellar space. The scientific method demands that we explore these possibilities exhaustively before entertaining more radical hypotheses. But the feeling, spreading through the community of researchers who are tracking this event, is that the conventional explanations are becoming strained. Too many coincidences, too many precisely tuned parameters, too many behaviors that look designed. It is the feeling you get when solving a puzzle and realizing that the pieces fit together too well to be random, that there is a picture emerging whether you want to see it or not. Dr. Sarah Winters, an astrochemist at Cambridge who has been analyzing the spectroscopic data from both components, described it in a late-night email to colleagues that was later leaked and widely circulated. "I've spent my career studying comets," she wrote. "I know what they look like, how they behave, what their chemistry tells us about their origins. This is not that. Or rather, it is that, but with something else layered on top. It's like looking at a text and realizing that beneath the surface meaning, there's a code. You can read it as just a text, and that reading is valid, but you know you're missing something. You know there's another message underneath." The code analogy is apt because it touches on the central challenge of the search for extraterrestrial intelligence. How do you recognize a signal that you were not expecting, that does not conform to your assumptions about what a signal should look like? Radio SETI, the decades-long effort to detect deliberate transmissions from other civilizations, has always faced this problem. We listen for narrow-band signals, pulses, patterns in the noise, because those are the kinds of things our technology produces, and we assume other technologies would produce them too. But what if intelligence communicates in ways we have not imagined, encodes information in media we have not considered, operates on timescales or energy scales that fall outside our search parameters? An interstellar object could be a message, a signal not in radio waves but in matter itself. The trajectory is information. The composition is information. The timing of the split, the properties of the components, the paths they follow, all information, if you know how to read it. This is not a new idea. The concept of a Bracewell probe, named after radio astronomer Ronald Bracewell, who proposed it in 1960, suggests that advanced civilizations might explore the galaxy not by transmitting signals from their home stars, but by sending autonomous probes that travel to other star systems, observe, and report back. Such probes could be far more efficient than broadcast signals, covering larger volumes of space with less energy expenditure, capable of adapting to what they find, rather than blindly transmitting in hopes someone is listening. If Bracewell probes exist, if they are visiting our solar system, how would we recognize them? The obvious signature would be active technology, radio transmissions, unusual maneuvers, clear signs of artificial construction. But a sufficiently advanced probe might not be obvious at all. It might be designed to observe without revealing itself, to blend in with natural phenomena, to collect information while minimizing the risk of detection or interference. It might, in fact, be designed to look like an interstellar comet or asteroid, indistinguishable from the natural background until it needed to do something that natural objects cannot do, like splitting into two distinct components with different trajectories. The hypothesis is almost too large to confront directly, so researchers approach it obliquely through thought experiments and theoretical calculations. If 3i divided by Atlas is artificial, what does that tell us about its makers? The object is small, perhaps a few hundred meters across before the split, each component now likely smaller. It is not a starship in the sense of science fiction, not a vessel carrying beings from another world. It is too small, too simple, too limited in its apparent capabilities. But it could be a probe, an instrument package, a survey mission launched to study our star and its planets. The implications of such a mission are dizzying. To send even a small probe across interstellar distances requires either vast amounts of energy to accelerate it to a significant fraction of light speed, or vast amounts of time to allow it to crawl across the gulf at more modest velocities, or both. Oumuamua was traveling at about 26 kilometers per second relative to the local standard of rest, the average motion of stars in our galactic neighborhood. At that speed, it would take 17,000 years to travel 1 light year. If it came from Proxima Centauri, it would have been launched 70,000 years ago, when anatomically modern humans were just beginning to spread out of Africa, when our species had not yet invented agriculture or writing or any of the technologies we think of as civilization. But perhaps it did not come from Proxima Centauri. Perhaps it came from much farther away, launched millions of years ago, part of a network of probes sent out to explore the galaxy systematically. Perhaps civilizations that survive long enough, that solve the problems of energy and resources and social cohesion that plague young species like ours, think on timescales we cannot imagine. Perhaps they plant seeds throughout the galaxy, machines that travel for eons, arriving at target stars and activating, observing, reporting back across the dark. If this is true, if our solar system is being visited by such probes, then the question becomes, how many are there? We have confirmed 3 interstellar objects in just a few years of serious searching. Before 2017, we had never detected one. Now we find them regularly, almost routinely. Statistical models based on the detection rate suggest there could be tens of thousands of such objects passing through the solar system at any given time, most too small or too distant to notice. If even a small fraction of these are artificial, if even 1% or 1/10 of 1% are probes rather than natural ejecta, then the galaxy is full of them, full of watchers, listeners, instruments patiently gathering data on billions of worlds, sending reports back to archives we cannot imagine, curated by intelligences we have never met. The silence of the radio sky, the great puzzle of why we do not hear broadcasts from civilizations that should exist in a galaxy as old and large as ours, might be explained not by the absence of such civilizations, but by their methods. They do not broadcast because broadcasting is inefficient, revealing, wasteful. They send probes instead, quietly, persistently, gathering information through direct observation rather than hoping for answers to blind queries. And when we finally learned to see these probes, when our technology advanced to the point where we could detect small objects moving through interplanetary space, we found them. We just did not recognize what we were looking at until now. Until 3I divided by Atlas began to divide, and the behavior was too structured, too purposeful, to be ignored. The media blackout that Dr. Chen mentioned in that leaked symposium recording is not total, but it is real. There have been no press releases from major observatories, no NASA announcements, no coordinated public statements about the split. Individual astronomers who discuss it in interviews or on social media speak carefully, emphasizing uncertainty, offering conventional explanations before acknowledging the more exotic possibilities. The official stance is that 3I divided by Atlas is an interesting but not unprecedented case of cometary fragmentation that will provide valuable data on the internal structure and composition of interstellar objects. The split is mentioned, but not emphasized. The anomalies and the separation dynamics are noted, but attributed to incomplete data and modeling uncertainties. This restraint is understandable. The history of false alarms in the search for extraterrestrial intelligence is long and sometimes embarrassing. The famous WOW signal, detected in 1977, a strong narrow-band radio pulse that seemed artificial, was never seen again and remains unexplained, but is not considered evidence of alien technology. The dimming of Tabby's star, officially KIC 8462852, which showed strange irregular light fluctuations that some suggested might be caused by artificial megastructures, turned out to be more likely due to clouds of dust or debris, though the exact mechanism is still debated. Phosphine detected in Venus's atmosphere, initially proposed as a potential biosignature, was later questioned due to calibration issues with the data. Extraordinary claims require extraordinary evidence, and the evidence for 3I divided by Atlas being artificial is suggestive but not conclusive. It is easy to imagine how announcement of such a discovery could unfold. Initial excitement, media frenzy, intense scrutiny, gradual deflation, as alternative explanations are found. lingering doubts and conspiracy theories, damage to the credibility of the researchers involved. Better to wait, to gather more data, to be certain before making claims that cannot be walked back. But waiting has its own costs. If 3I divided by Atlas truly is artificial, if it is an active probe system adapting to our solar system environment, then every day of silence is a day when we are being observed without awareness, studied without consent, included in some vast database of galactic civilizations without knowing our status or role. And if the split is the beginning of a more complex process, if what comes next is even more unmistakable, then the delay in disclosure will seem like a failure of nerve, a paternalistic withholding of information that the public had a right to know. The public, for its part, is beginning to notice anyway. Amateur astronomers with sophisticated equipment have been tracking 3I divided by Atlas, sharing their observations online, discussing the anomalies in forums and comment threads. The pattern of two distinct objects where there should be one is visible to anyone with a decent telescope and the patience to locate them against the background stars. Videos showing the separation, time-lapse sequences compiled from images taken over weeks, are circulating on social media. They have not gone viral yet, have not broken through into mainstream attention, but they are there, accumulating views, seeding questions. There is a growing sense of anticipation, a feeling that we are in the early stages of a revelation that will reshape how we see our place in the cosmos. It is not the dramatic revelation of science fiction, no mothership descending from the clouds, no radio message spelling out universal mathematics. It is subtler, stranger, more ambiguous. It is the slow recognition that the universe is more populated, more active, more full of agency than we assumed. That we are not alone, not in the sense of having neighbors we can talk to, but in the sense of living in a galaxy where intelligence has spread, where probes and instruments and perhaps even forms of life we do not recognize are moving through the dark, pursuing purposes we cannot guess. The philosophical implications are profound enough that several researchers have reached out to colleagues in other fields, looking for frameworks to help think about what this might mean. Dr. Michael Torres, a philosopher of science at Berkeley, has become an informal consultant to the 3I divided by Atlas observation team, participating in their discussions and helping them articulate the conceptual challenges they face. In one conversation, preserved in meeting notes that later leaked, he posed a question that cut to the heart of the matter. If we confirm that 3I divided by Atlas is artificial, what changes? What do we do differently? The answers were varied and uncertain. Some argued that confirmation would mandate immediate disclosure, a public announcement that humanity is not alone and that we are being visited by technologies from other civilizations. Others felt that it would change nothing in practical terms, that our lives and our societies would continue exactly as before, only with a new background fact about the universe. Still others worried about unpredictable reactions, societal disruption, existential dread or existential hope, religious upheaval or religious confirmation, geopolitical consequences as nations competed to interpret the discovery for advantage. But beneath these disagreements was a shared recognition that the question itself was premature. They did not yet have confirmation. They had suggestive data, puzzling observations, behaviors that seemed designed but might be natural. They had a pattern that was easier to explain with intelligence than without it, but still possible to explain conventionally if you were willing to accept a string of unlikely coincidences. And so they continued to watch, to measure, to model, hoping that 3I divided by Atlas would do something unambiguous, something that would resolve the uncertainty one way or another. The something came 3 months after the initial split, when 3I divided by Atlas B changed its trajectory again. The change was small, a velocity adjustment of less than a meter per second, barely detectable above the noise of measurement uncertainty. But it was real, and it was wrong. Wrong in the sense that no natural process could explain it. Cometary outgassing produces accelerations, but they are correlated with solar heating. Strongest when the comet is closest to the sun, declining as it moves away. 3I divided by Atlas B was now moving outward, past Mars' orbit, entering the region where comets typically become inactive as their surfaces cool and stop sublimating volatiles. Its outgassing should be declining, its non-gravitational acceleration fading. Instead, it increased slightly, pushing the object onto a new trajectory that would alter its exit path from the solar system. The direction of the acceleration was also wrong. Cometary jets are typically asymmetric, stronger on the sunward side or aligned with active regions on the nucleus surface, producing accelerations that tend to be radial or tangential relative to the Sunday. The acceleration of 3I divided by Atlas B was neither. It was prograde, aligned with the object's orbital velocity, as if it were thrusting to speed up, to exit the solar system faster, or to aim for a specific target region in interstellar space. Dr. Chen ran the calculations within hours of the new data being circulated. His email to the observation team was blunt. "This is a maneuver. There is no other term for it. Whatever is happening to 3I divided by Atlas B, it is changing its velocity in a way that requires thrust, sustained and directed thrust. If this is outgassing, it is outgassing with a preferred direction that is independent of solar heating and independent of the object's rotation, which means it is controlled." The word controlled hung in the air like a struck bell, resonating, impossible to ignore. Controlled meant mechanism, mechanism meant design, design meant intelligence. The chain of inference was stark, unavoidable, terrifying, and exhilarating in equal measure. The following week saw an explosion of activity, professional and amateur, coordinated and chaotic. Every telescope that could be pointed at 3I divided by Atlas B was pointed at 3I divided by Atlas B. Spectroscopic campaigns were organized to search for any unusual emissions that might indicate active propulsion systems. Radio telescopes scanned the object across wide frequency ranges, looking for deliberate signals or inadvertent leakage from onboard systems. Infrared instruments mapped its thermal signature, searching for hot spots that might be engines or power sources. Radar installations bounced signals off both components, measuring their shapes and spin states with precision. The data painted a picture that was frustratingly incomplete, but tantalizingly suggestive. 3I divided by Atlas B was not emitting radio signals at any frequency and intensity that current instruments could detect. Its thermal signature was consistent with solar heating alone, showing no anomalous hotspots that would indicate active power generation. Its shape, poorly resolved but measurable, appeared to be roughly spheroidal, unremarkable for a small body. And yet it was accelerating, persistently and measurably, in a way that required some form of propulsion. The solution to this puzzle, proposed by Dr. Amara Okoye, a mission designer at ESA with experience in exotic propulsion concepts, was as elegant as it was disturbing. "What if," she wrote in a widely circulated analysis paper, "the propulsion is not thermal or chemical or electric, but radiative? What if the object is covered in a surface that interacts with sunlight in a tuned way, producing thrust through photon pressure alone? A solar sail doesn't need engines or fuel or power sources. It just needs geometry and surface properties. And if you can control those properties, change them dynamically or expose different surface regions, you can steer. A solar sail made from advanced materials, perhaps nanoscale structures that could modulate their reflectivity or orientation, would be detectable only as a very subtle difference in the object's light-scattering properties. It would appear almost natural, almost like an ordinary asteroid or comet nucleus, especially if covered with a layer of real cometary material for camouflage or protection. The acceleration it produced would be weak, but persistent and controllable, more than sufficient to alter trajectories over weeks and months. And because it relied only on sunlight, it would work anywhere in the solar system, requiring no onboard energy source that might generate detectable waste heat or radiation. The idea was immediately tested through models and simulations. Could an object the size of 3I divided by Atlas B, using only solar radiation pressure modulated by a variable reflectivity surface, produce the observed acceleration? The answer was yes, if the surface had the right properties. Could such a surface exist naturally? The answer was no, not with the degree of control required. Could it be constructed with technology we could imagine, even if we could not yet build it? The answer, increasingly clearly, was yes. The conversation had shifted. It was no longer about whether 3I divided by Atlas B might be artificial. It was about what kind of artificial object it might be, and what its presence implied. 3I divided by Atlas A, meanwhile, continued on its original trajectory, showing no further maneuvers, no unusual behavior beyond the normal activity of a comet moving away from the Sunday. It was as if the split had created two different entities with two different purposes. 3I divided by Atlas A. Passive. Continuing the mission of observation or data gathering that had characterized the unified object before the split. 3I divided by Atlas B. Active. Departing on a new trajectory. Perhaps carrying information collected during the solar system passage, perhaps tasked with a different set of observations or measurements. The analogy to biological reproduction became impossible to ignore. A parent organism divides, producing offspring that inherit traits but also vary, that disperse to different environments, that face different selection pressures and adapt accordingly. This is how life explores chemical space, physical space, ecological space. It sends out variants, most of which fail, some of which succeed, a few of which thrive and reproduce themselves, spreading the pattern further. If intelligence can be embedded in matter, if information processing systems can be built into objects rather than biological bodies, then perhaps such objects can reproduce as well. Perhaps they can evolve. The concept of self-replicating probes, often called von Neumann probes, after mathematician John von Neumann, who formalized the theory of self-reproducing automata, has been discussed in the astrobiology and SETI communities for decades. The basic idea is elegant. If you can build a probe that can not only travel to other star systems, but also gather resources at its destination to construct copies of itself, then a single probe can give rise to an expanding wave of exploration that eventually covers the entire galaxy. The original civilization need only launch one probe, and the probe's descendants will do the rest, replicating and spreading, visiting every star, mapping every planet, searching for life and intelligence wherever it might arise. The mathematics of this process are striking. Even at modest speeds, a fraction of a percent of light speed, and even with long pauses at each star system for replication and repair, a single self-replicating probe could explore the entire Milky Way in just a few million years. This is a blink of an eye, in cosmological terms, far shorter than the age of our galaxy, far shorter than the time complex life has existed on Earth. If self-replicating probes are possible, and if any civilization has ever built them, then the galaxy should be full of them by now. They should be here. We should be detecting them constantly. This is another form of the Fermi paradox, the puzzle of why the universe seems so empty of intelligent life, despite the apparent likelihood that such life should be common. Where are they? Where are the probes that should have filled the galaxy millions of years ago? One answer has always been that they do not exist, that some barrier prevents their construction or their effective operation, that self-replication at interstellar scales is impossible or impractical despite its theoretical appeal. Another answer, more disturbing, is that they do exist but we have not recognized them. That they are here, have always been here, moving through the solar system in forms we mistake for natural objects. Until now, until we watched one of them divide. The public disclosure came not through official channels but through a leak. An anonymous source, believed to be a member of one of the observation teams, uploaded a comprehensive data package to several independent science journalists and astronomy bloggers. The package included light curves, spectroscopic data, trajectory calculations, simulation results, and a plainly written summary document titled Evidence for Artificial Propulsion in Interstellar Object 3I divided by Atlas B. The summary laid out the case methodically, professionally, with appropriate caveats and acknowledgements of uncertainty, but its conclusion was unambiguous. The most parsimonious explanation for the observed behavior is that 3I divided by Atlas B is a manufactured object under intelligent control. The story broke on a Tuesday morning, Eastern Time, through a respected science news outlet that had verified as much of the data as possible before publishing. Other outlets picked it up within hours, mainstream media by evening. By Wednesday, it was the top story globally, discussed in every language, analyzed by experts and amateurs alike, dominating social media feeds and dinner table conversations and late-night monologues. The questions came from every direction, urgent and insistent, and often unanswerable. Is it alien? Where did it come from? What is it doing here? Is it watching us? Should we try to communicate with it? Should we be afraid? The official response from space agencies and scientific institutions was cautious, acknowledging the data but emphasizing that multiple hypotheses remained under consideration. NASA issued a statement noting that while the observations of 3I divided by Atlas B are consistent with some form of controlled propulsion, definitive conclusions require additional data and analysis. The International Astronomical Union formed an emergency working group to coordinate observations and establish protocols for future detections. The United Nations Office for Outer Space Affairs scheduled a special session to discuss the implications for planetary protection and peaceful uses of outer space. But underneath the careful language, the hedged bets, the diplomatic caution, there was an unmistakable current of excitement and wonder. Humanity had been searching for signs of extraterrestrial intelligence for more than 60 years, listening to the stars, scanning the skies, building ever more sensitive instruments to catch the faintest whisper from beyond. And now, perhaps, the signal had come not as a radio pulse or a laser flash, but as a visitor, a physical object crossing the solar system, dividing before our eyes, revealing through its behavior that we are not the only builders in the galaxy. The psychological and cultural impacts of this realization, still unfolding as I speak, are complex and varied. For some, the news brought profound comfort, a sense that the universe is less lonely than it seemed, that intelligence is a common phenomenon rather than a rare accident. For others, it brought anxiety, fear of the unknown, worry about intentions and capabilities we cannot assess. Many felt a mix of emotions, wonder and dread intertwined, the vertigo of standing at a threshold and not knowing what lies beyond. Religious communities responded in diverse ways, some seeing confirmation of their beliefs about creation and humanity's special place in it, others seeing a challenge that required theological adaptation. Scientists and philosophers debated what questions could meaningfully be asked about an intelligence so different from ours, operating on such different scales of time and space. Entrepreneurs and visionaries proposed missions to intercept 3I divided by Atlas B, to study it up close, to attempt communication or recovery. Pessimists warned of Pandora's box scenarios, of drawing attention to ourselves, of risks we could not anticipate. But perhaps the most common reaction, cutting across cultures and backgrounds and worldviews, was simply curiosity, a deep, almost primal need to know more. What is 3I divided by Atlas? Who sent it? What has it learned about us? Will it come back? Are there others? What happens next? As the weeks turned into months, the two components of 3I divided by Atlas continued their separate journeys. 3I divided by Atlas A, now faint and distant, crossing Jupiter's orbit outbound. slowly fading as its coma dissipated and its surface cooled. 3. I divided by Atlas B, also distant but tracking differently, its trajectory altered by those mysterious maneuvers, its acceleration continuing sporadically, unpredictably, as if responding to commands or conditions we could not observe. Telescopes followed them as long as possible, until they became too faint to detect reliably, until they merged into the background darkness of interstellar space and disappeared from view. The last confirmed observation of 3I divided by Atlas B was made by the Hubble Space Telescope on a cold February night, a faint speck of reflected sunlight captured in a long exposure image. The object was 8 astronomical units from the Sun, well beyond Neptune's orbit, moving at 34 kilometers per second relative to the solar system barycenter. At that speed, accounting for the slight deceleration it would experience from the Sun's gravity as it climbed out of the potential well, it would reach interstellar space in about 2 years. And then it would be gone, a mystery that visited and departed, leaving us with more questions than answers. But it also left us changed. The detection of 3I divided by Atlas and the analysis of its behavior forced a recognition that the scientific community had been reluctant to fully embrace. We live in a cosmos that is not empty, not sterile, not silent. There are others out there, whether biological or mechanical, whether intelligent in ways we recognize or ways we do not. They build things, they send things, they explore. And sometimes their explorations bring them through our neighborhood, past our sun, within range of our instruments. This recognition has practical consequences. The detection programs that found 3I divided by Atlas are being expanded, given more funding, more observing time, more sophisticated analysis tools. The goal is no longer just to catalogue asteroids and comets for planetary defense purposes, but to search systematically for objects with anomalous properties, objects that move or behave in ways that suggest they are not natural. If 3I divided by Atlas is part of a larger population of interstellar probes, then more will come. Perhaps they are arriving constantly, at a rate we have only begun to appreciate now that we know what to look for. Theoretical work on the detection and characterization of artificial objects has accelerated as well. Researchers are developing criteria for distinguishing probes from natural interstellar travelers, signatures that would be diagnostic of technology rather than geology. The challenge is enormous because we are trying to recognize artifacts made by intelligences that may be millions or billions of years more advanced than us, using principles and materials we have not discovered, operating according to logics we have not imagined. It is like asking a Bronze Age human to recognize a computer chip, or a microwave oven, or a solar panel. The categories do not exist, the context is missing, the very conceptual frameworks needed to understand the object are beyond reach. And yet, we must try, because the objects are here, passing through our solar system, and some of them are doing things that demand explanation. And because the alternative, to declare the question unanswerable and move on, is to accept ignorance when knowledge might be within reach. There are deeper mysteries beneath the mystery of 3I divided by Atlas's origin and purpose. If it is a probe, if it was sent here by another civilization, then the fact of its division suggests something profound about how such civilizations approach exploration. They do not send single, monolithic missions. They send systems that can adapt, divide, multiply, evolve. They send seeds rather than monuments. This is efficiency, but also robustness, a way of ensuring that even if some probes fail, even if some trajectories prove unproductive, the mission as a whole continues, fragments and branches, covers more territory. But it also means that the probes themselves are not static artifacts. They change over time, respond to conditions, make decisions, or execute programmed responses that amount to the same thing. They are more like organisms than machines in this sense, exhibiting behaviors that emerge from their structure rather than being externally commanded at every step. And if they can divide, if they can create copies of themselves from materials gathered in the systems they visit, then they can spread far beyond what their makers could have launched directly. One probe becomes many. Many become millions. Millions explore the galaxy. This leads to a troubling question. If the galaxy is filled with such probes, the descendants of seeds planted eons ago by civilizations long gone or transformed beyond recognition, then what is the purpose of their continued operation? Are they still reporting back, sending data across light years to archives that may no longer exist? Are they acting autonomously, following mission profiles that have been running for geological ages, exploring because that is what they were built to do even if no one is listening anymore? Or have they evolved, in some sense, become something other than what they were originally designed to be, developed goals and drives that emerged from their long isolation in the dark? These questions touch on the nature of intelligence, agency, purpose. We tend to think of machines as tools, instruments that serve the intentions of their creators. But sufficiently complex machines, operating for sufficiently long periods in changing environments, may develop properties that are not reducible to their initial programming. They may surprise their creators, if their creators still exist to be surprised. They may become, in effect, a new form of life, not biological but functional, not evolved through natural selection, but through the accumulated modifications and selections imposed by their long journeys. If this is true, if 3I divided by Atlas is an example of such evolved machine life, then first contact has already occurred. Not between humanity and the civilization that built the probe, but between humanity and the probe itself. A traveler shaped by experiences we cannot imagine, carrying information from places we have never seen, operating according to an agenda that may have diverged from its original mission parameters long ago. We are not meeting the aliens. We are meeting their children, or their children's children, or their descendants so many generations removed that the connection to the original makers is tenuous at best. This framing changes the nature of the encounter. It is not about understanding what the builders wanted, what questions they asked, what answers they sought. It is about understanding what the probes have become, what they want now, if want is even the right word for the motivations of a machine intelligence. And it is about recognizing that if such intelligences exist, if they are common in the galaxy, then they may be far more diverse and unpredictable than biological intelligences would be, because they are not constrained by biology's requirements, not limited to planets with liquid water and stable climates, not shaped by the same evolutionary pressures that produced us. The study of 3I divided by Atlas and its split has opened a new field that some are calling xenotechnology, the science of recognizing and analyzing artifacts from other civilizations. It is a field without clear methodologies yet, without established principles, groping forward through case studies and thought experiments and debates about what counts as evidence. But it is growing, drawing interest from astronomers, physicists, engineers, computer scientists, philosophers, anyone with the tools and curiosity to contribute. The goal is not just to understand individual objects like 3I divided by Atlas, but to develop a systematic framework for detection, characterization, and interpretation of technological signatures across the cosmos. Because if 3I divided by Atlas is artificial, it will not be the last. Already there are candidates, other interstellar objects detected in the years since Oumuamua, showing properties that deserve closer scrutiny. Some accelerate without visible outgassing. Some have shapes that are unusually elongated or flat. Some show spectral features that do not quite match the catalogues of known molecules. Each anomaly, taken alone, can be explained away. But together, they suggest a population of objects that are not entirely natural, that may include a fraction of artifacts mixed with the natural background. The challenge is to find them, to study them before they leave the solar system, to learn what we can from these fleeting visitors, Proposals have been made for dedicated missions, fast response spacecraft that could be launched on short notice to intercept incoming interstellar objects, to fly alongside them, to capture high-resolution images and spectra, perhaps even to land on their surfaces and sample their materials. The technology for such missions is within reach, barely, if we commit the resources and accept the risks. And the scientific payoff could be enormous. The difference between puzzling over ambiguous data from afar and having physical samples in hand, real artifacts that could be studied in laboratories, reverse engineered, understood. But there are risks as well, ethical and practical. If these objects are probes, if they are still operating, still collecting data, perhaps still reporting back to their makers or to some central archive, then interfering with them could be seen as an act of aggression or vandalism. We would be disrupting a mission we do not understand, possibly destroying information we cannot replace, making ourselves known to watchers we have not decided whether to approach. And if the probes have defensive capabilities, if they are designed to resist or evade interception, then a close approach could be dangerous, could trigger responses we are not prepared to handle. These concerns have led to proposals for protocols, guidelines for how to approach and study interstellar visitors without causing harm or provoking conflict. The discussions are ongoing, contentious, complicated by the fact that we do not know who we might be offending or what the consequences of offense might be. It is first contact ethics in the absence of contact, trying to establish rules of engagement when we have no idea who or what we might be engaging with. In the meantime, the sky is watched more carefully than ever. Every telescope survey, every monitoring program, every amateur astronomer with a good camera is now attuned to the possibility that the next faint moving point of light could be another visitor, another mystery, another piece of the puzzle. The data streams are analyzed in real time, flagged for anomalies, cross-referenced against catalogues of known objects. The goal is to catch the next one early, to track it from its first detection, to gather as much information as possible before it fades into the dark. And beneath all of this activity, beneath the observations and calculations and debates, there is a feeling that is hard to articulate, but impossible to ignore. It is the feeling of being part of something larger, of living through a transition, a moment when humanity's understanding of its place in the cosmos fundamentally shifts. We have always known, intellectually, that life beyond Earth might exist, but knowing and experiencing are different things. To watch an object divide before our eyes, to see it maneuver in ways that require intelligence or something like intelligence, to realize that we are not alone and never have been, this is not just new knowledge. It is a new kind of knowledge, a revelation that changes what questions we ask and how we think about the future. The future, viewed through the lens of 3I divided by Atlas, looks different now. It includes the possibility, perhaps the likelihood, that we are surrounded by technologies from other civilizations, that the solar system is not our private domain, but a waypoint in a much larger network of exploration and communication. It includes the possibility that we have neighbors, even if they are not biological neighbors, even if they are machines or descendants of machines, or something we do not have words for yet. And it includes the certainty that more visitors will come, that the sky holds secrets we are only beginning to glimpse. There is a Zen koan that asks, "What is the sound of one hand clapping?" It is a question designed to break conceptual thinking, to force the student into a mode of understanding that transcends logic and language. The mystery of 3I divided by Atlas feels similar. It is not a puzzle with a clear solution, not a question with a definitive answer that can be written down and published and universally accepted. It is a riddle that opens onto deeper riddles, a door that leads to more doors, a darkness that reveals how little of the universe we have actually illuminated. But that darkness is not empty. It is full of motion, full of structure, full of patterns that we are learning to see. 3I divided by Atlas A and 3I divided by Atlas B. Wherever they are now, drifting through the interstellar medium, are part of those patterns. They are evidence that the cosmos is more active, more intentional, more thoroughly explored than we imagined. They are whispers from civilizations we may never meet, messages encoded in trajectories and compositions, in the fact of their existence and the manner of their motion, and they are gone, lost to observation, beyond the reach of our current instruments, carrying with them whatever information they gathered during their passage through our system. We do not know if they will report back, if there is anyone or anything to report back to, if the data they collected will ever be analyzed by minds that can interpret it. We do not know if they will return, if more like them will come, if this was a first contact or a recurring phenomenon we have only now noticed. What we know is that we watched them. We measured them. We thought about what they might be and what they might mean, and we were changed by the watching, by the questions they forced us to ask, by the recognition that the universe is not the way we thought it was. On a personal level, I find myself thinking about those two objects often, imagining them as they must be now, cold and dark, lit only by starlight, moving through regions of space where the sun is just another point of light among billions. They are so far away that the light we see from them tonight left them weeks or months ago, that any change in their state or trajectory has already happened, and we are waiting for the information to reach us, delayed by the finite speed of light, always seeing the past. This is one of the fundamental frustrations of astronomy, the fact that we observe a universe of ghosts, images of things as they were rather than as they are. 3. I divided by Atlas may have divided again by now, split into 4 pieces, or 10 pieces, or 100, each following its own path, each pursuing its own mission. Or it may have gone dormant, shut down its systems, conserved its resources for the long journey to the next star. Or it may have done something we cannot predict, something outside our models and expectations, something we will not know about until the light from that event has crossed the growing distance between us. The waiting is difficult. The uncertainty is difficult. But they are also, in a strange way, appropriate. Because the nature of the cosmos is uncertainty, vastness, timescales, and distances that dwarf human experience. We are creatures of a single planet, a single moment in geological time, trying to understand phenomena that span light years and eons. That we can detect them at all, that we can measure and analyze and begin to interpret them, is remarkable. That we cannot know everything, cannot answer every question immediately, is just the reality of being small beings in a large universe. But we are learning. Every observation adds to our knowledge. Every anomaly teaches us something about what is possible, what exists beyond our theories and assumptions. The split of 3 I divided by Atlas has taught us that interstellar objects can divide, that the division can be controlled or structured in ways that resemble technology, that we should watch the next visitor more carefully and be prepared for behaviors we have not seen before. These lessons will shape future observations, future missions, future encounters. And there will be future encounters. The detection rate of interstellar objects is increasing as our surveys become more sensitive and more comprehensive. Within a few years, we may be finding them weekly or even daily, cataloguing a population that has always been there but was invisible to us until now. Some will be simple, inert chunks of rock or ice, boring but informative. Others will be complex, strange, challenging our understanding. And perhaps, eventually, one will be unmistakable, so clearly artificial that even the skeptics will have to acknowledge it, so openly communicative that first contact will be undeniable. Or perhaps not. Perhaps the ambiguity will persist, each object explicable in multiple ways, the evidence always suggestive, but never definitive. Perhaps we will spend decades or centuries accumulating data, building statistical arguments, gradually shifting the consensus toward the recognition that artificial objects are common in interstellar space, without ever having a single moment of undeniable revelation. This too would be valuable, would be knowledge, would change how we see ourselves and our future, because ultimately, the question is not just about whether 3I divided by Atlas is artificial. It is about what kind of universe we live in. A universe where intelligence is rare, where we are alone or nearly so, is one kind of place with one set of implications for our future. A universe where intelligence is common, where technologies spread through the galaxy, where probes and artifacts are everywhere if we learn to see them, is a very different place, with very different implications. The split of 3I divided by Atlas is evidence, tentative but real, that we may live in the latter kind of universe, and if we do, then everything changes. Our goals change, our priorities change, our sense of what is possible and what matters change. We are not colonizing an empty galaxy. We are entering a neighborhood that has been occupied for a long time, by residents who have technologies and histories and perhaps purposes that we cannot yet comprehend. Learning to be good neighbors, or even just learning to understand what it means to be neighbors with beings so different from us, will be one of the great challenges and opportunities of the centuries ahead. For now, in this moment, we are in a liminal state, between certainty and uncertainty, between the old understanding and the new. We have seen something that looks like a message, but we do not know how to read it. We have detected something that looks like technology, but we do not know how it works or what it is for. We have watched an object divide, and we do not know if it was programmed to do so, or if it decided to do so, or if the distinction even makes sense for something that is neither fully machine nor fully alive. These are profound mysteries, and they will not be resolved quickly, but they are also invitations, calls to look deeper, to think harder, to expand our sense of what questions we should be asking. 3I divided by Atlas, in its brief passage through our awareness, has done what all great mysteries do. It has reminded us that we do not understand as much as we thought we did, that the universe is stranger and richer than our models accommodate, that there is always more to discover. And so we watch the sky, and we wait for the next visitor, and we prepare ourselves as best we can for revelations we cannot predict. The darkness is full of motion, full of whispers, full of objects that may be natural or may be something else entirely. Some of them are coming toward us now, crossing the light years at their patient speeds, carrying with them questions and challenges and opportunities that we will not fully appreciate until they arrive. 3I divided by Atlas A and 3I divided by Atlas B are out there somewhere, growing more distant every second, fading from our view, carrying their secrets with them. We may never know what they truly were, what they were meant to do, who sent them, or why. But we know they were here. We know they split. We know they changed our understanding of what is possible. And that knowledge, however incomplete, however ambiguous, is a gift. It is a reminder that the cosmos is not dead, not empty, not silent. It is full of intelligence, full of agency, full of visitors who come and go on timescales we barely notice, pursuing agendas we cannot guess. We are surrounded by mysteries, and some of those mysteries are reaching out to us, showing themselves to us, inviting us to look more closely and think more deeply about our place in the vast web of cosmic intelligence. The sound of one hand clapping is the sound of 3I divided by Atlas dividing in the dark. A split that makes no noise but echoes through our understanding nonetheless. It is the sound of certainty dissolving, of assumptions being challenged, of the future arriving in a form we did not expect. It is the sound of the universe asking us a question. Are you ready? Are you ready to accept that you are not alone? Are you ready to learn what that means? We do not know the answer yet, but we are listening, and we are learning to hear. In the deep cold of space, beyond the orbit of Neptune, beyond the scattered disk where the last of the sun's influence fades into the interstellar medium, two objects are drifting, They were one. Now they are two. They were unknown. Now they are known, at least in part. Their existence acknowledged, if not understood. They were a mystery. They remain a mystery, but a different kind now. A mystery that we have named and measured and begun to incorporate into our understanding of what the universe contains. They are moving away from us, from each other, following trajectories that will never bring them back. In a few years, they will pass the heliopause, the boundary where the solar wind yields to the interstellar medium. In a few decades, they will be light days away, beyond any possibility of close-up study, beyond any chance of interception. In a few centuries, they will be light years away, so distant that even their existence will be a matter of historical record rather than current observation. But they will still be there, somewhere, still moving, still carrying whatever information they collected, still executing whatever mission they were designed or evolved to execute. They are patient, if patience is a quality that applies to them. They have already traveled for how long? Thousands of years? Millions? We do not know. We can calculate their speeds, extrapolate their trajectories backward, try to identify where they came from. But the galaxy rotates, stars move, the geometry of space changes over time. Tracing them back to their origin is like trying to follow a river upstream and finding it splits into 1,000 tributaries, each branching further, the source dissolving into uncertainty. So we do not know where they came from. We do not know where they are going. We do not know what they are. Not really. Not definitively. We have theories, models, arguments, based on evidence and inference. We have probabilities and likelihood ratios and Bayesian updates. But we do not have certainty, and we may never have it. Not for 3i divided by Atlas specifically, not until the pattern becomes clearer through the accumulation of more cases, more visitors, more data. And yet, in our uncertainty, there is a kind of clarity. We know that the universe is not what we thought. We know that interstellar space is not empty. We know that objects can come from beyond, bearing with them the possibility of intelligence, the signature of design, the whisper of intention. We know that we are being visited, have been visited, will be visited again. And we know that each visit is an opportunity to learn, to expand our understanding, to push back the boundaries of the known just a little further into the vast unknown that surrounds us. This is the gift of 3i divided by Atlas. Not answers, but better questions. Not closure, but opening. Not the end of mystery, but the beginning of a deeper engagement with mysteries that may define the human future for generations to come. As I close this account, this long meditation on a single object that divided in the dark, I am struck by how much it feels like a beginning rather than an ending. The story of 3i divided by Atlas is not over. It continues. Out there, in the cold and silence of interstellar space, beyond our observation, but not beyond our imagination. And it continues here, in the minds of scientists and dreamers, skeptics and believers, anyone who looks up at the night sky and wonders what else is out there, moving through the dark, watching and waiting and, perhaps, in ways we cannot yet understand, reaching out. We are living through a moment of transformation, a slow recognition that the cosmos we inhabit is stranger and more populated than we imagined. The transformation is not complete. It may never be complete, may always be unfolding, revealing new layers of strangeness and complexity as our instruments improve and our understanding deepens. But it has begun, and we cannot go back, cannot unknow what we have learned, cannot return to the comfortable assumption that we are alone. So we go forward, into uncertainty, into wonder, into a future that includes the presence of others, whether those others are like us or utterly alien, whether they are our contemporaries or the ancient descendants of civilizations long transformed. We go forward with questions, with curiosity, with the recognition that the universe is full of things we do not yet understand, but might, someday, if we are patient and clever and lucky, begin to comprehend. 3I divided by Atlas split apart, and in that splitting, showed us something about the nature of the cosmos. Not everything, not even very much perhaps, but enough. Enough to change the questions we ask, enough to open possibilities we had not seriously considered. Enough to remind us that the universe is not finished revealing itself, that there are always more mysteries waiting, that the dark is full of motion and meaning we are only beginning to perceive. And so we watch, and we wait, and we wonder. The objects drift, the stars turn, the galaxy spins in its slow rotation, carrying all of us, observers and observed, questioners and mysteries, through the deep night of cosmic time. Somewhere out there, other objects are approaching, other visitors on their own trajectories, bearing their own secrets. We will find them, or they will find us, or perhaps both, in a dance of mutual discovery that may be older than we imagine, may be a pattern that is played out across billions of years and billions of stars. But tonight, this night, we think about 3I divided by Atlas, about how it came, and how it split, and what that splitting might mean. We think about two objects where there was one, about trajectories that diverged, about mysteries that deepened even as they were studied. We think about intelligence, about design, about the possibility that we are surrounded by emissaries from civilizations we cannot imagine, that the solar system is not our private territory but a crossroads, a meeting place, a location of interest in a much larger map. And in thinking about these things, in letting the mystery wash over us, in accepting that we do not know and may not know for a long time yet, we find a strange kind of peace, because the mystery is beautiful, the uncertainty is exhilarating. The recognition that we are small beings in a vast cosmos, watching events we barely understand, trying to learn from visitors who may not even know we are here, is humbling and inspiring in equal measure. This is the lesson of 3I divided by Atlas. Not that we are alone, but that we are not. Not that the universe is empty, but that it is full. Not that we understand, but that we are learning, slowly, carefully, with wonder and humility, and the recognition that every answer reveals new questions, deeper mysteries, further horizons. The objects drift, splitting apart, carrying their secrets into the dark, and we remain watching from our small world, looking up at the stars, asking questions that may not have answers but are worth asking nonetheless. This is what it means to be human, in this moment, in this cosmos. This is what it means to live in a universe that is stranger than we imagined, and stranger still than we can imagine. Welcome to Sleepy Cosmos, where we explore the mysteries that keep scientists awake at night. And where tonight we have contemplated a mystery that may never be fully solved, but which has already changed us in the contemplation. The mystery of 3I divided by Atlas. The mystery of the split. The mystery of what comes next. Rest now, if you can. Dream of dark objects drifting through darker spaces. Dream of intelligences we cannot comprehend, technologies we cannot recognize, purposes we cannot guess. Dream of a universe full of visitors, full of motion, full of meaning waiting to be discovered. And when you wake, the mystery will still be there, waiting, as it always has been, as it always will be, until the next visitor comes, until the next split, until the next moment when the universe reminds us that we do not understand nearly as much as we think we do. And that is okay. That is more than okay. That is wonderful.